a.m., so probably we should start our first session. So I would like to welcome you warmly. As you probably noticed, my name is Krzysztof Kalma. I work in Szczecin, northwestern Poland, at the West Pomeranian University of Technology, at the Department of Signal Processing and Multimedia Engineering. We will have 4 papers. As far as I know, 1 presenter is missing, so probably 18 or maybe 20 minutes maximum for the presentation should be enough. Our first presenter will be Mr. Grzegorz Debita from Poland, from Wrocław, and the paper is entitled Quality Evaluation of Voice Transmission using BPL Communication System in MV Mine Cable Networks. There are 6 authors,
yes.
as you can see, from different universities and institutes and companies. So please, the floor is yours.
Thank you, Mr. Chairman, for the great introduction. Okay. Ladies and gentlemen, our work is about our research is about the quality of experience, the voice transmission using a middle voltage cable in technology BPL technology communication. And some outline, there will be some introduction to the BPL PLC technology, because BPL is the one of the part of the power line communication. Something about underground environments, because that environment is a different in a normal environment, for example in propagation. Something about the test, the quality evaluation, what type of the signal samples we are using, what type of test coordinates, the results and comments and some conclusion. Okay, BPL communication is the part of PLC, power line communication. That power line communication is consists of 2 technology. One technology is some low up to 115 kilohertz and the high. That means high. The frequency is not very high, yes, because now we have trends. We have the very high frequency, gigahertz. We are frequency between in this case 2 to 7 megahertz, yes, because we are using the modems from the market. This application is consists of to the elements when we can buy from the market now. That is not the optimized device. Yes, we only make the measure how it will be if we, for example, using that technology to transmit the voice. And in this technology we have many problems. The problems is, for example, with analog parameters. In analog domain we have many noises. We have the problem with characteristic impedance in this area of frequency, because it's not stable, and etc. and etc. For effective transmission in BPL, for example, using the very important is the decoupled parameters, the attenuation and the characteristic impedance. And we are use the frequency for that experiment using the channel, that is the channel 2 by 7 megahertz, because the producers of the modems have that frequency is to use. And that frequency was optimal for this type of cable what we have. Because firstly, we are make some mathematical model is to show what is the propagation. Yes, I'm the author of this model. Of this model, yes. And from our calculation is that that frequency is optimal for that type of the cable. And in this mining in KGHM Polska Miedź S.A. That is the block schema, the points where we have the modems. Yes? First is the point A and B in shaft, yes, and underground. But we are from this paper we are prepare the research between 2 points A and B in the mining in the land 300 meters. And what is the point? If this temperature is changed, the parameters of propagation inside this cable is changed too. The characteristic impedance is changed, the noises is changed, and we are make our research of this type of parameters. Yes. Now, if we are going to that mining, yes, and we are make the review, the temperature will be other, yes, and we have we don't have the same results. Okay, we are make our research in 2 cases. One is we are doesn't on that cable is doesn't current and doesn't anything working, yes, anything another devices, and that is the situation where we can use that cable, for example, like emergency channel, yes, when we have some damage underground. And the second point, we have some test bed when we have the devices is working on that transmission line, and we are using two type of the coupling, because in BPL technology we have the induction coupler, and that coupler is installed. I show you on the next picture, yes, how it look like and how install it. The topology is point to point where we have the master gateway and the slave gateway. To prepare our experiment, we have computer where we have the installed Linux operating systems, and we have the DHCP server, and there on this computer we have the tools, open source tools, to prepare a voice server, and here in the shaft we have the microcomputer like Raspberry Pi. That was Raspberry Pi, and there is tool. There is the informatic tools which we can use to prepare the communication between this computer and this microcomputer from point B to point A, and then from B to point A, the samples. And another type of coupling we have connected the capacitive and induction coupling test. We are, and that is working too. We can, for example, have the capacitive coupler and the receiver have using the induction coupler. And how it look like? That is the capacitive coupler. That is here. That is the Faraday transformer. No, not the coupler. That is the Faraday transformer. That is the couplers, and that is the inductive coupler. That is the inductive coupler in point A. That is the capacitive couplers of point A, and from point B, you see that is the inductive coupler is directly in this direction. And next, okay, that is about tools. We are use Ubuntu in the last stable version. We are use iSky software for the voice server and VLC software to have receiver. And we are prepared dedicated scripts, dedicated software yes, to make the automatic voice transmission. And the parameters is the bitrate is from 8 to 14 kilobits per second, where we have the 5 different bitrates: 8, 16, 24, and etc. Yes, and that samples has took 10 minutes respectively. And now, when we make that that experiment, yes, the second point is we find the Przemek Falkowski from Politechnika Gdańska give 15 people in aged between 25 to 23 years old, and they are to check the quality of experience yes, of that samples. And the signal samples, there was in 3 languages: British, English, German, and Polish. What is important? That samples files is from the source from ITU. That is the dedicated samples, for example, to testing the telephones, digital audio broadcasting, and we use that samples from the ITU, from ITU recommendation. And what is interesting? Because we have the speech signal samples where we present the 5 different bit rates, yes, and we are use OGG algorithm coding, and that signals are transmitted over IP, not only by BPL but over IP. And we will see that the test some quality. What is the point? As a single session for the listener was approximate to 20 minutes. Yes, we have the 15 listener took our and make the become the study and the audio familiar with the test scenario. Yes, all these people have the same handphones. Yes, Bidynamic Custom 1 Pro. That is the name of the company. Yes, of that handphones. And the results on figure I show you what is the result and what is interesting? Because the bit rates 8, 16 and 24 we are qualified to analyze this because the higher bit rates don't change it. And then show that is for 8 kilobits. That is the mean opinion score parameter. If that parameter is higher, that quality of that quality of experience is better. Yes, you see for the 8 kilobits per second is, I know, worse. Not good. It's not good. But for 16 kilobits per second, it's good. For 24, better. That we'll see for we doesn't need higher, yes, because that is. Thank you, Sean. Okay, we are going to conclusion. I think for that you will see that according to obtained results, a clear and understandable voice message can be provided for the bit rate equal to 24 kilobits per second, and that is the point. And why that work is important is you see on that slide we are using now we are using the modems, the devices from the market. Next step is prepare and develop own integrated modem, yes, dedicated modem, where we can optimize all algorithms, signal processing, demodulation, codings, and the voice compression inside, because for that work is very interesting for an emergency situation in the mining. Because if we have emergency situation, for example, aircraft underground, we doesn't have the communication. Using, for example, that type of couplers, I can give the group of the emergency group give that modems, for example, in the knapsack, yes, and there can build it the emergency network communication. Next type, next point of view is military, because the soldiers need very fast create new alternative way to communication. And I think that's it all.
Okay, thank you. And now we will start the discussion. Feel free to ask any questions. We have enough time. Maybe I should start the discussion. So, well, quite interesting idea. From my point of view, the most interesting thing is the assessment of quality of the voice data, because it was subjective, and I wonder if there are maybe some objective tools for this purpose or not, and maybe there are some dedicated, maybe recommended by the ITU data sets similar like for images. Maybe there are such data sets for objective and subjective as well, quality assessment of voice signals, and maybe there could be the possibility to use a kind of automatic text voice recognition at the output of your system.
Yes, of course. We want to prepare the testers from some dedicated groups.
Yeah.
Like the miners, for example, but we need a very big group to make that research firstly, and using something machine learning or another algorithm, yes, to make the automatic algorithm according, for example, the IT recommendation. Yes,
Okay.
that will be the next part. That will be the next part of that work, because now that work is doesn't granted for any project. Yes,
Yeah.
that is the
For sure,
our. Yes, we doesn't have finance now,
Yeah.
but we will be applied, yes, to the national center to apply for that work to optimization, yes, and for that to make the automatization, yes, to change the quality.
Probably the database of some
Yes,
signals.
of course,
with
of course.
Subjective assessments. It will be a good idea. And I'm wondering one more thing. Why OGG? Because there are some military standards for the voice compressions, like as far as I remember, FR 1014,
Yes.
FR 1015. Probably you know them.
Yes.
Why haven't you used such approaches?
Now we are use OGG firstly because it's very popular in internet radio.
Yeah.
And that was the first point.
Okay.
We need to check many codecs. Yes, we got C++, yes, the military codecs, of course. That is the small part. That is the small part of the work, very small.
Yeah, but it's a good starting point. Okay, so any other questions? If not, thank you once again.
Thank you.
And we go to the second presentation. The second presentation is entitled Automatic Detection of Heartbeats in Heart Sound Signals Using Deep Convolutional Neural Networks. The authors come from Slovenia, and the presenter will be Mr. Grega Wybańczyk.
Yes, thank you, Mr.
Please,
Chairman.
the floor is yours.
Thank you for the introduction. So good morning, everyone. My name is Grega Wybańczyk, and today I'll present to you our paper titled Automatic Detection of Heartbeats in Heart Sound Signals Using Deep Convolutional Neural Networks. So my presentation is structured from the following sections. Firstly, we'll go through the introduction and describe the problem which we are addressing. Then I'll present our proposed method. Afterwards, we take a look at the experiments we conducted, and later on see the results of the conducted experiment. And finally, I conclude my presentation with some final thoughts and possible future work. So signal segmentation is considered to be one of the fundamental problems of digital signal processing in various information monitoring, prediction and control systems in a wide range of fields such as seismology, astrology or medicine. Observing the existent segmentation methods, they most commonly utilize more or less complex techniques to extract features from the signal, such as frequency analysis or wavelet transformations, and later on perform some kind of classification over them, usually using some kind of more conventional classifier, such as decision trees. However, these approaches, especially in the field of the medicine, have not performed very well due to the interpatient variations of biomedical signals, leading to the inconsistent performance of such methods. So, in recent years, the hybrid segmentation methods are utilizing the feature extraction capabilities of the deep convolutional neural networks and are gaining the momentum. So based on those observations, we set our main goals to construct a fully automatic method utilizing deep CNNs for the feature extraction and classification task without requiring any expert knowledge and while achieving the at least comparable results to hybrid methods utilizing the CNNs, tackling the task of detecting the heartbeats from the highly viable sound signals. So our proposed method primarily consists of the following three phases. So first phase is the signal processing phase. The second is building and training the deep convolutional neural network. And in the last phase, post-processing, we are calculating the exact location of predicted heartbeat. So firstly, let's present the data set we used. We used a collection of annotated heartbeat sound signals initially prepared for classifying Hard Sounds Challenge by Peter Bentley et al. In 2011. The dataset consists of 21 sound clips captured with the iStethoscope Pro iPhone application. It can be seen on the image. The clip length varies between 1 and 30 seconds with a sampling rate of 44.1 kilohertz in a VAW encoding. So recordings were captured in highly variable environments with excessive background noise, and like I said, obtained using the iStethoscope Pro iPhone application, utilizing the iPhone's integrated microphone. So just to give you a bit of a perspective of it, what kind of sound quality are we dealing with, and on the image below are marked points where the integrated iPhone microphone was located while recording the heartbeat sound signals. So the first signal pre-processing phase, the first we did from the raw heartbeat sound signals, we performed the z-score normalization. The A and B images are showing the unnormalized sound signal, and the C and D respectively showing the signal after the z-score normalization. So next step was splitting sound clips. Each sound clip was divided into multiple frames. We used the non-sliding window algorithm. We set the window size to the 6,615 samples, or 150 milliseconds. The step size was 1/3 of the window size, with around 2,205 samples, or 50 milliseconds. We picked this window size based on the ANSI WM EC38 and EC57 standards, which basically describes if the detected heartbeat location is in range of 150 milliseconds plus minus, the detected sound heartbeat is deemed to be accurate. So, and the image below is representing the sliding window algorithm which we used. So here is the architecture of our convolutional neural network. So we utilize the not so standard one-dimensional convolutional layers. What's the difference between the classic two-dimensional convolutional layer and this one-dimensional convolutional layer? Basically, they work in the same manner. The only difference is that one-dimensional convolutional layer has the second dimension equal to 1, and basically the sliding kernel computations, convolutional computations are only in horizontal direction, as in two-dimensional they are sliding in two directions, so horizontally and vertically. So at the input we are feeding our neural network with those splitted windows of sound signal, and then we have two pairs of convolutional and maximization pooling layers followed by the fully connected layer. And at the end we have output layer with single neuron with sigmoid activation function, which is labeling the fed sound frames into the heartbeat or no heartbeat, basically 1 or 0. So next phase was the last phase was the post-processing phase, where we determine the location, the exact samples in the heartbeat sound clip in which the heartbeat occurred. So from the CNN we obtained the predicted class, so heartbeat or no heartbeat, and also the prediction probabilities for each of the classified frame. Then we follow this three-step procedure where we have the array of predictions for each frame, and we observe for the occurrence or sequence of occurrences of positively classified frames. So from those observations we create so-called candidate ranges of splits, and from each candidate ranges of splits we select the one frame which has the highest probability to consist the heartbeat inside, and then we, from this frame, we select the sample point in the middle of the split and set it as the predicted location of a heartbeat. So in order to properly evaluate the performance of our proposed method, we performed gold standard tenfold cross-validation methodology. Basically, we divided 21 sound recordings into 10 disjoint parts or folds. Then we trained the CNN with 9 out of 10 folds and test the performance on the remaining 1 fold. So then we repeat this procedure 10 times, each time testing the performance with a different remaining fold. And at the bottom are the CNN training parameters. We utilize the efficient mini-batch approach, setting the batch size to 256 sound clips, and we train the CNN for the 150 epochs using the Adam optimizer with initial learning rate set to 10 on -3rd. So, given the specifics of the problem, we adapted the performance metric from the dataset challenge in addition to the conventional classification metrics such as accuracy, specificity, sensitivity, and F1 score. So the adopted metric was average distance from the real heartbeat locations, which is denoted as delta K. So basically, it's average distance by the absolute distance of the real and predicted heartbeat. So the image below is representing the one whole sound clip. The blue color is showing the sound signal, and the red vertical line is the real position or location of the heartbeat, and the green one is our predicted heartbeat location. So in this image, all of the predicted heartbeats are within 150 milliseconds plus minus range. So here we're reporting the average distance metric as described in previous slide. The average the delta total is representing the sum of delta metric over all sound clips in each fold, and the delta average represents the average the distance over the all sound clips. So what we can see that the minimum delta average distance is around 3 milliseconds, the maximum delta average is around 528 milliseconds, and the mean distance is around 186 milliseconds. When we're comparing the sum delta total with other methods, our method is better performing, and on average around 80.5% of predicted heartbeats are in plus minus 150 millisecond range defined by ANSI WAMI standard. Here is the classification performance of the proposed method. So the accuracy over each fold varies from 70 to 87% with a standard deviation of around 5%. Our method achieved better balance of sensitivity versus specificity, or F1 score, while comparing to other methods with a standard deviation of 9.37%. So to conclude, we have presented a new method for the automatic detection of heartbeats in heart sound signals using deep convolutional neural networks. It works in a fully automatic, straightforward manner, does not require any pre-processing techniques to extract features from the signal or any medical domain knowledge. It is evaluated against the sound signals captured in highly variable environments with excessive background noise, and compared to the existing methods evaluated on the same dataset, our method outperforms other methods. So for future work, based on those promising results, we would like to extend our work to apply more advanced algorithms for the calculation of the predicted heartbeat locations. And we will also like to improve the classification performance of our CNN, introducing different learning strategies, as well as utilize some hyperparameter optimization methods for fine-tuning the CNN model. So thank you for your attention. If you have any questions, please.
Okay. Thank you very much. And I would open the discussion. Please.
Okay. I have the questions. The analyzing of that signal, that was in the time domain, yes?
Yes, time domain.
Okay. And why do you not analyze this in the frequency domain using Fourier analysis?
Yeah, of course. There are researchers that utilize the frequency domain, Yeah, but we have better results evaluating the time domain, not frequency domain.
That is
Yeah, that was quite interesting. The previous.
quite interesting, but do you check only the amplitude or amplitude and phase?
Only amplitude.
Only amplitude.
Yeah.
But the phase is very interesting.
Yeah,
Because
of course.
if you analyze amplitude and phase, you have the all information about the signal in frequency domain.
Yeah, of course. That could be the possible future work too.
Is I think for example, many time ago, man who is named from Poland, Jan Zarzycki, is invented the optimal filtration methods.
Yes.
That is the method that we can create the filter with the adaptive transmutation parameters, and maybe to find some distortion of your signals, because your signals is a bit, yes?
Yeah.
If the parameters of the bit is changed, the transmutation must be changed. Maybe that method will be to find tell us 0 or 1
Yeah.
that we have some distortion or not.
Yeah, of course. Yeah, that could be possible future work. Yeah, thank you.
Okay. Any other questions? Well, personally, I would say that the results are very surprising for me,
Yeah.
personally, because in much more complicated tasks, analyzing the images using CNNs, there are much better results.
Yeah.
So personally, I wouldn't ever think about using such not so deep CNN, because 5
No,
years.
no. Yeah, it's quite standard.
Another
Yeah.
classical approach from 1970s, rather than
Yeah.
deep CNNs. So, 80% accuracy without any shape analysis, only finding the position of the signal is not very good.
Yeah.
Okay, I know that it could be just a starting point for further research, but probably combining maybe with frequency-based analysis, using more classical approach, probably you would go to more successful results, even for noisy signals. There are some tracking algorithms also with the data hidden in noise, so probably it could be even simplified.
Yeah, of course. Our view or angle from which we are seeing the problem is, me personally, I'm not the signal expert or working on this area. So our main goal was to find out if we can at least achieve comparable results using the fully automatic way, utilizing the CNN to detect some heartbeats. Yes, and we didn't research so much into the classical traditional methods, how we could combine them into our approach to gain even better results. Our main goal was to find out if the convolution network itself could be used to extract or detect heartbeats from the highly viable sound signal. So if you have maybe more knowledge about the signal processing, it would be quite useful to integrate those features.
We can try to discuss, but
Yeah.
in general, I would say that this is the example of, I would say, the sign of the times. People tend to use CNNs for everything, as it would be a solution of each problem, and sometimes just piece of knowledge related to the problem is much more useful than just using the CNN when you have no idea what is inside.
Yeah, that's
because you
that's true. It's black box method. Yeah,
of
it's
each
black
layer.
box.
Okay.
Yeah. But nevertheless, we obtained the results which were better than the existing researchers. That was quite interesting as well.
So probably the hybrid method in future will be the point.
Probably the hybrid will be the best. Gathering together both best sides. Yeah.
Okay. It could be good classifier, for example.
Yeah, of course.
So after the pre-processing,
of course.
Even differentiation of the signal should help. As the input data. Okay.
Yeah. Thank you.
Any other questions? Okay. Thank you once again.
Thank you.
And now we will go to the third presentation from Saudi Arabia. The presenter will be Siet Imtaz Haider, if I pronounce this more or less properly. The title of the paper will be Detection and Classification of Baseline Wonder Noise in ECG Signals using Discrete Wavelet Transform and Decision Tree Classifier. Please,
Thank you, Mr. Chairman.
20 minutes.
My name is Saeed Haider, and today I'm going to present our research titled Detection and Classification of Baseline Wonder Noise in ECG Signals using Discrete Wavelet Transform and Decision Tree Classifier. The outline of my presentation is as follows. I will start with the motivation behind this work, then I will give a brief introduction about the topic, and after that I will discuss the proposed methodology, followed by the results and the conclusion. Now, whenever we acquire ECG signal or any biomedical signal, usually there is a noise in the signal. So in our work we are focusing on only the baseline wonder noise, and the reason is because it shares the same frequency as that of the ST segment of the ECG signal. So it is very important to estimate the baseline wonder noise prior to its removal. The ST segment provides the useful information in different clinical detection of heart diseases. So we can see, for example, in this we can see there is a large baseline wonder noise, and in this example this is a baseline free signal. So we should distinguish between baseline free signal and baseline wonder noise signal. Now, if we have a good estimation of the baseline wonder noise, we can prevent that segment from filtering, and it will preserve the actual features of the ECG signal. Now, this figure actually it might not look very clear, but if, for example, if there is a noise-free signal, and if we use a high-pass filtering, then it might slightly alleviate the ST segment of the ECG signal. It's not very clear, but like usually when we use the high pass filtering, the ST segment is alleviated if there is no baseline wonder noise. So the important thing is that we should not filter the segment of the ECG signal that is noise free. Recently, like what people are doing, they have the ECG signal and they use the high pass filtering on the complete signal, and the noise is removed, but if some part is noise free, then it will alter the shape of the signal. So to the main motivation is to identify the segments of the signal that have minimal or no baseline wonder noise, and this identification process will assist in preserving the clinical relevance of baseline free segments by not applying any filtering technique. So the introduction about the topic, baseline wonder is one of the major low frequency noises, and the range is well below 0.8 Hertz, and the main causes of this noise is patient movement, respiration, muscle contraction, and electrode impedance change. So a care must be taken while eliminating this noise, as the low frequency region of the ECG spectrum is highly susceptible to distortion. The American Health Association, they recommend the cutoff frequency should not be more than 0.05 Hertz to preserve the possible distortion, but this frequency can be relaxed up to 0.67 Hertz as long as the linear phase of the filter is preserved. Now, about the proposed methodology, our main idea is to classify each segment of the ECG signal into minimal, moderate, or large baseline wonder noise, and the proposed algorithm comprises of 5 stages. The first stage is that we have a complete signal which is of more than 30 minutes length, so we partition each signal into 5 seconds, and then we perform the downsampling of the each segment, and after that we are doing the wavelet decomposition and reconstruction, and we are actually using the approximate coefficient at level 6 using COI5 mother wavelet transform. Then we are doing the magnitude estimation of the baseline Wonder noise, and finally we are constructing the decision tree classifier. So the first part is the segmentation without overlapping. The objective of the segmentation is to break the input signal into multiple fragments and analyze them separately. In the literature, we have found that if we use a segment size of 5 seconds or 7 seconds, the performance of ECG signal quality classification results in a very good, gets good results. So we have considered a segment size of 5 seconds. Next is the downsampling. As we know that the most of the ECG spectral power is located below 30 Hz. So using the Nyquist sampling theorem, we can downsample the data to 60 Hz or greater, which is the desired frequency in our case. And since we are already dealing with the low frequency noise, so even some part of the high frequency is like we can still use this 60 Hz method. So the database which we have used, they have acquired the signal at 360 Hz. So we can downsample it by a factor of 5, which will result in 72 Hz, which is still slightly larger than the Nyquist criteria. Yeah. About the discrete wavelet transform, here's an equation which we can use to find the number of the level of decomposition which we need, and here Fs is the new sampling frequency, which is 72 Hz in this case. So it will result in 6 levels, and here we can see that the approximate coefficient at level 6 is within the frequency range of 0 to 0.56 Hz, which is still within the range of the recommended by the American Health Association. So here we have a comparison between various mother wavelet transforms. We can see that the COI5 wavelet outperforms the other because it has the lowest normalized sum square residual and the highest cross correlation coefficient. About the here we can see that this is the original signal, and this is the first segment of the signal, and here it is the sampled ECG signal with the this dotted line shows the baseline estimation using COI5 mother wavelet. For the estimation of magnitude of the baseline Wonder noise, we are using some basic mathematical equations. We are calculating the range of the approximate coefficient, then we are performing the mean centering, and next we are finding the standard deviation of the mean centered approximate coefficients, and after that we are estimating the magnitude of the baseline Wonder noise by calculating the cumulative sum, and finally we are calculating the area under the curve using the trapezoidal method, and this area under the curve is actually for the cumulative sum of approximate coefficients. So for those segments that have minimal or no baseline Wonder noise, they should have a smaller value of area under the curve, and those segments that have a high baseline Wonder noise, they will have a larger value of area under the curve. And finally we are constructing a decision tree classifier. For that we are using C4.5 decision tree algorithm using Vecca data mining tool, and there's an open source implementation of this method already available in Vecca, which is J48, and this method is based on the divide and conquer approach. So that means it will select the main attribute and then it will partition the segment into subsets. For our classifier we have main 3 attributes, and the first is the range, the second is the standard deviation of the mean centered coefficients, and the last is the area under the curve of cumulative sum of squared mean centered approximate coefficients. We are using the MIT BIH arrhythmia database, which is a very well-known database. It has a total recordings of 48, and each recording is slightly larger than 30 minutes. And we are partitioning each recording into 5 seconds non-overlap segments. That means we have a total of 361 segments for each record, and so that means for all the recordings we have a total of 17,328 segments. For the training purpose, we are using the data set of 36 patients, 36 recordings, and for the test purpose we are using the 12 ECG recordings. Here is the parameters gain ratio, which is for the decision tree classifier, and here we can see that area under the curve, it has a maximum gain ratio. So that means the decision tree classifier select this attribute as the parent attribute, and then it will do the classification. So here is the constructed decision tree classifier. We can see that the area under the curve is selected as a parent attribute, and then the tree is made. Yeah, so this is the complete proposed methodology. So we have a ECG signal record, and we are partitioning it into 5 seconds non-overlap sampling. Then we are downsampling each segment. Then we are extracting the approximate coefficient at level 6, and we are doing a mean centering, finding the standard deviation of the mean centered approximate coefficients. Next we are finding the cumulative sum, and based on that we are calculating the area under the curve. So these three features, the range, standard deviation and area under the curve, they are going for the classifier, and we are using 36 recordings for the training purpose and the 12 records for the test purpose. So 48 records, the sampling frequency is 360 Hertz, and each record is slightly longer than 30 minutes, and there are 361 segments for each record. So here we can see the results, like for example for this MIT arrhythmia database record number 205, this is the segment number 5, and here we can see that the baseline noise, there is an offset, so we can simply remove the offset by mean centering, but we do not need to filter this kind of signal because it has a very low baseline wonder noise. And we can see that here we have a large baseline wonder noise, and the area for this kind of segment is around more than 6,500, but for a low baseline wonder noise the area is around 28. Yeah, here we can see that for the complete recording of recording number 123, the segment number 22, it has a maximum range and the maximum area under the curve. So that means in this complete recording, segment number 2 has the maximum baseline wonder noise. Similarly for this recording, we can see that the segment number 221, it has a maximum range and maximum area under the curve. So that means this segment has the maximum baseline wonder noise. For the test purpose, we are considering 2 recordings, and there are 3 adjacent segments, and this is the range, standard deviation and area under the curve for these 3 segments. So in the next slide we'll see record number 123, and there are 3 consecutive segments here. Now this is the segment. If we look at this figure, we can see that there is a very small baseline wonder noise, then we have a very large baseline wonder noise, and then we have a slight baseline wonder noise, but we cannot say that this is a baseline free signal. So by applying our method, we can see that it has found that this is the minimal baseline wonder segment, this is a large baseline wonder segment, and this is a moderate baseline wonder segment. So this is the confusion matrix for the test data. We can see that there are still some inaccurate predictions, and we can see that there are still many segments that have a large baseline Wonder noise, but still there are some segments which have low baseline Wonder noise, and these we should make sure that we should not filter these kind of segments. This is the class-wise sorry, this is a class-wise performance of the classifier, and we can see that the sensitivity for the minimal is around 92%, and for the moderate and large it is around 99.5%, and the accuracy is around 99% for the minimal, 98.9% for the moderate, and around 99% for the large. So in conclusion, we have achieved high accuracy in identifying the minimal, moderate and large baseline Wonder segments, and the proposed method can possibly be used in devising an algorithm to optimize the baseline Wonder removal problem, and in future we can develop a selective filtering method, and this work can serve as a pre-processing stage, and once we know that which segments we have to filter and which segments we have to not filter, then using this technique we can simply achieve the better accuracy, because we will not be filtering the part of the segments that is baseline free, and we will be only focusing on the segments that are that have baseline Wonder noise, and we will be achieving the better trade-off between accuracy and computational cost. So that's the end of my presentation, and if you have any questions I would be happy to answer. Thank you.
So I will start the discussion. Feel free to ask.
Okay. I have a question. You are using samples from the MIT database.
Yeah.
Okay. Tell me what part of the time that samples is prepared.
Sorry, can you repeat?
From what part of the time?
Yeah.
That is the probes, for example, the samples from this year, second year.
It's a very old database. This is the very renowned database.
And now the technique of the measure is changing. If you have, for example, analog devices have developed the new type of analog to digital and digital to analog converters, when many effects what you have of that samples of that probes are eliminated.
Okay.
If you now make, for example, some test using the modern hardware, you have, I think, better results, because many effects what
they
you
are
have,
already removed.
yes, that distortions,
Yeah.
and then there will be eliminated in hardware.
Okay. Yeah. So this is a good.
Okay. So it was just a remark. Probably.
Yeah.
So I would have another one, because I wonder why haven't you compared your approach based on wavelets? Of course, there were the Debatry wavelets and so on. Could be Haro or some others. Doesn't matter. Maybe Mexican had, but you haven't used Fourier analysis, and it would be probably a more natural way to analyze such signals than the wavelets. So, what would be the results? Do you have any initial results using Fourier analysis, or you just take wavelets and everything is fine?
Yeah, actually we only use the wavelets. We didn't look at the Fourier transform, but
Surprising.
yeah, we haven't used the Fourier, but we directly used the wavelet transform, and we did the comparison between the wavelet transforms, and we selected the best wavelet from there.
Okay, but there is a chance that using Fourier analysis you can get just better results without wavelets. So it's first thing that you should check, in my opinion.
Yeah.
I always wonder about the name of the sampling theorem. It is Nyquist or Shannon. Maybe the Nyquist is rather frequency, but it doesn't matter. Maybe there are two names. Yeah. Okay, they're equivalent. So, any other questions? If not, let's thank once again.
Thank you so much.
And the fourth presentation is missing, unfortunately. We will have no presentation from India, but we will have the fifth presentation. The authors are missing as well, but we have the substitution, probably. And the title of the paper is Extraction of Novel Features Based on Histograms of MFCCs used in emotion classification from generated original speech dataset. So another paper about the voice signals. The authors are Muhammed Bakirek, Mahir Atmis, Selman Kulac, and Umut Ulutak from Turkey. And the substituting presenter should present yourself.
Yeah.
Okay.
Thank you. Hello everyone. I am Osman from Turkey. Actually, I am not original presenter in this presentation. Mohammed was the presenter, but he couldn't come to here because of some problems. Mohammed and I are PhD student in same university, and we have same supervisor, Selman Kulac. They are included in the paper, but I didn't. So I don't have information actually about this presentation. Because of this, I will not take any questions from you. But if you have questions or suggestions for this, I request that you send an email to authors. An email address was given at the end of the presentation, by the way. Yes, talk about the study. I think, as I know, this study is about actually prediction, emotion prediction from speech signals, as I know. The presentation is outline of the 8th section. First, introduction and what's the problem and motivation, and solution, and how the experimental workflow, and what's the databases, Berlin and Pau databases, and their known feature, what's their known features, and experimental results and conclusions. Human and computer interaction systems have been drawing attention increasingly in actually recent years. Understanding the emotions of humans plays significant role in these systems. In the study, there are two main contributions. One is their novel feature, which is MFCC's, multi-frequency spectrum coefficients, representation based on their histograms. Other contribution is Pell speech data, whose emotions are labeled and cross-checked by PhD students. What's the problem? Problem branching claims that emotions are categorized as the primary emotion and the secondary emotions. Primary emotions, anger, fear, sadness, disgust, surprise, anticipation, trust, and joy are fundamental basis for secondary. What's the motivation? In the study, emotion of sadness, happiness, and natural are aimed to be recognized by their design systems. Develop a database to compare with existing database and test their framework. What's the solution? Their known MFCCs based coefficients are utilized as feature vectors. SVM, support vector matching, with cross-validation are employed as a classifier because of limited data. In the main part of this solution, firstly, all data sets are acquired to calculate the MFCCs for each individual file. Then the first, second, and the third features of each file are calculated using MFCCs values for each elements. The last one for solution, covariance matrix and a label vector for output immersion classes are generated by SVM. After the SVM analysis, accuracy and confusion matrices are calculated as a mean value for all items. Experimental workflow is totally 6 steps. First, collect speech data, then pre-process speech data, and extract speech features, and the others separate training and test features, and tune classifier on training features, and the last predict emotion on test feature. Yeah, this table shows that Perlin and Perl databases. These databases are composed of audio speech data. Table 2 shows the details of these two databases, including audio language and gender, emotion, emotion type of speech. And type 3 gives more details of how databases which is created in this study. It's composed of a variety of videos, audio data. We can see their known features. Instead of average of MFCCs and their first and second derivative, they use more informative version of MFCCs using their PDF and values shown as below. This novel feature provides smaller size of data for histogram representations and requires less computational power. Their experimental results, table 5, 6, and 7. Table 5 for Berlin databases, table 6 Paul databases, and the last one is the combined databases of these results. These results in first feature, average of MFCCs and their derivatives. Second feature, their null features, and the third feature is contact first and second features. By the way, Berlin database is better than other scenarios since fixed sentence and same environment is used for people. Yes, its conclusion. Its conclusion is about 5 steps. The first, best results are achieved by the Berlin database compared to PAL database because the sentence for the speech in Berlin data are the same for each individual and they are performed in the same framework as well. Generated their own data set to build comprehensive framework. Due to the lack of abundant amount of data, SVM outperforms DNN, and according to LIRD, I think they gave the references. Their study has better results than average classification accuracy of SVM for the speech emotion classification studies. And the last one, thanks to their novel features based on histogram of MFCCs, they have obtained better results from the experiments. Since distribution of all MFCCs values has so much more information to represent the emotion rather than using only average of MFCCs. Yes, all of this presentation is enough. If you have any questions, you can send an email. These email addresses, it is the original presenter.
Okay, so
Okay.
thank you.
Okay, thank you.
Maybe, probably there will be no questions addressed to you, but maybe there will be some remarks during the discussion.
You said that you get better, well, not better result than other models, yes?
Yeah.
Can you evaluate how much better?
But I didn't say anything. I didn't include this paper I just present instead of
You
my,
don't know anything about it.
yeah.
I would have some remarks, and maybe you could forward them to the authors. Maybe they will be helpful, maybe not, because I know that probably only 3 states of emotions are recognized because of the databases used, and Berlin looks simpler, and the results are better for Berlin database, so it's obvious. But I wonder if there are only such 2 databases available. Maybe there are some newer, better databases, including more emotions, and maybe it could be the next step.
Yeah.
But there are some works, even at my faculty. I was reviewing the PhD thesis related to emotion recognition using video or image analysis and modeling of emotions on human faces. So maybe a good idea will be the combination of recognition of the emotions from the speech with the video data. So maybe such a joint hybrid idea will be very good for the PhD or some other better articles, maybe joint with someone. So maybe this would be the most significant value from this discussion, but maybe there is another remark.
Another remark is the database from Paul Ekman. Paul Ekman is that is the theory of micro-expression of face, and that is the correlation with micro-expression and what we now talking, yes, because we the voice, the information in many situations is not
visible.
Yes, it is not correlated, not correlated with what we have the expression of the face.
Yeah, if you are a good actor, sometimes you can try to do this. Yes, so the voice is a bit different than
very people.
The expression
Many
of the face.
people who lying.
Yeah.
Many people who lying. That is that situation. That the emotion on the face is not correlated. Is inverted correlation.
Yeah.
It is the inverted correlation.
So maybe the police will be interested in
Yeah.
this. Yeah, okay. So thank you once again for presentation. And as far as I know, the session is closed. So thank you for active participation in this session. The next one will be at 11 a.m. The chairman will be Linas Vilainis, and now we should 45 minutes for a coffee. Thank you.
Thank you.
Colleagues, we are about to start. We have 5 presentations in our section, and probably you remember the rules. The presentation is 1 minute.
Yeah, it's okay. It should be great.
After yesterday's part, we should do that. No, I think all the presentations are very interesting, and I was speaking with some colleagues. They are hunting some of the presentations to see, so look out for the questions. I'm Linas Vilenis. I'm from Kaunas University of Technology, so I will be your chair. And if you remember, if I'm showing you 3 minutes, so you should scroll pretty fast. But you still have time. But if it is 1 minute, so you should jump to the conclusion. So actually, you have 15 minutes, so more or less it's plenty of time. And I call first presenter Mikhail Prauschek. And Mikhail will present how to power batteryless devices from nothing. Perpetuum mobile. Actually, the title is Powering Batteryless Embedded Platforms by Piezoelectric Transducers, a pilot study. So, the floor is yours, please.
Okay. So thank you for a great introduction. So my name is Michal Krauzek and I come in from the Technical University of Austria, Czech Republic, and I am going to present the cooperation of our university and University of Alberta. It's a pilot study of powering batteryless embedded platforms by the piezoelectric transducers. So this is my presentation outline. So first I will explain the research context and present the general topologies of harvesting wireless sensor networks. Then I will introduce the piezoelectric converter itself, and I will describe the experimental setup. And in the experimental part, I will explain the R firmware, present the overview of the result, and I will conclude and I will show you some future work outline directions. So, the research context on this work is the broad topic, because we have a long-term project aim of ultra-power electronics, energy harvesting, Internet of Things communication, intelligent sensors, and all is applied in the environmental or industrial monitoring. So basically we are doing the smart sensors for environmental monitoring or the industry for the factories. In this topic, we are using three topologies. So the first topology is the batteryless system without any energy storage. The second, using the energy storage module, and we have 2 conversions module. And the last one, using the batteries. So in this particular work, I'm using the second one. So we are using the harvesting module. We are harvesting energy from the piezoelectric domain. And then we are convert the energy to the storage module represented by the capacitor, and after that we are convert this stored energy to the dissipation module represented by the MCU board. So first I would like to present the converter itself. So our solution use the energy harvesting for the vibrations. And this kind of energy varies depending on the amount of kinetic energy generated by the source. So in general, the source is some mechanical energy. So in this contribution, we are evaluating the possibilities of piezoelectric transducers usage to powering microcontroller-based embedded systems. So we are using to power some microcontroller board. So this transducer is based on the direct piezoelectric effect, and it can be exposed to vibration with the constant or varying frequency. So in this solution, we are using the constant frequency to simulate the result. So we do some construction of the experimental setup. We are using the piezoelectric transducer based on the piezoelectric tip. And we have the electrical motors, which is rotate by the frequency of 1.33 Hertz. The resonance frequency of the piezoelectric element is about 10 Hz. So you can see on the graph, we are starting in the time 0.5 seconds. We are hitting the tip, and after that we are variating in the resonance frequency of piezoelectric's tip. So in general, the amplitude of the output voltage is around 35 volts plus minus. So we are generating pretty much high voltage on this kind of the transducers. So our testing setup is look like this. We have input kinetic energy, we have our piezoelectric tip, and we are using the integrated circuit LTC 3588. So it's a rectifier of the piezoelectric energy, and it has the DC-DC converters to output capacitor. So in general, we are converting the input energy through the rectifier. We are storing in the capacitor with the capacitance of the 100 microfarad. And we are trying to remain the constant voltage on the output capacitor to power our MCU board. So this is our MCU board. Maybe you are familiar with. So it's a Freedom board KL25Z. It equipped with a high performance ARM Cortex M0 Plus microcontroller, and it's also very low power. So we are implementing two modes. We are implementing the very low power run mode, and we are implementing the very low power stop mode. So in the very low power run mode, we have current consumption around 700 to 800 microamps, and in the stop mode we have something around 15 microamperes. In very low power run mode, we are running a testing firmware. For these purposes, we implement the 7th order field filter to test all possibilities of the MCU, because it's implement the digital signal processing instructions. So we want to use this kind of features. So we are switching between the very low power run mode and stop mode in some predefined intervals. So it looks like this. We have this finite state machine. We are starting in the init mode. We initialize peripherals, and after that we are going to the run mode. After we finish the calculation of the filter parameters, then we are going to stop mode. We are setting the low power timer, and after 4 seconds we are going back by the wake up instruction, and we are going back to the run mode. If we have no energy, then we are going to the shutdown, and after we are obtaining an energy, we are going to the init again. So, results of the experiment. We are measuring 3 parameters. We are measuring the supply current to development board. We are doing the time log of energy storage voltage and the time log of output capacitor voltage, so we can estimate the input and output energy. For this reason, we are using the precise picoampermeter. So, in general, we are doing the 3 experiments. The first experiment describes the charging of the system. So we have no load applied in the setup. So we are charging by electric motor by the piezoelectric element. So you can see the output voltage of the capacitor, and also you can see in certain time, about 8 seconds, the DC-DC converter in the integrated circuit starts working, and we are remaining about 1.8 volts on the output. The second experiment includes the load, so we are calculating the filter. So we are starting operating, and we are charging the output capacitor. But in this time, you can see we have the power consumption from the MCU, and you can see the switching the run and stop modes. So the system is running, and we are doing our operation, and also if we still rotating the motor, the energy storage is charging, and it's working definitely as perpetuum mobile because it's working with the infinite input of the energy. But due to lower efficiency of the DC-DC converter, we have some state when the incoming energy and efficiency and outcoming energy is in the balance. So this is proof it's working on this kind of input energy. And first experiment is discharging. So we try to obtain information how long can operate without the input of the energy. So we start on the reference state of charge. It's around 11 millijoules, sorry, on the 15 volts of the energy storage voltage. And we did the 6 cycles to completely depleted the energy storage. So in this case, it works around 24 seconds. So this is the overview of the result. We do 10 trials run for each experiment. And what is interesting here? So first interesting thing is we measure the very low power run current and very low power stop current. And we do it for the 2 input voltage. These currents are almost are very similar. So in this case, the 1.8 voltage is much better because the total power consumption is low due to the dynamic properties of the system. And on the other hand, the efficiency of DC-DC converters is better in the 3.3 volts solution. That means if you're using for application to withdraw much current, the total utilization of the energy is better in the case of the 3.3 volts of output voltage. So, what are the conclusions here? We try to explore the possibility of use of piezoelectric energy to powering the battery system. So we have 2 observations. The first is, as I said, the 1.8 voltage solution has the significantly lower power consumption. And second conclusion is in the reverse of the first observation. So if you are using the higher voltage of the output capacitor, you can utilize more energy. So, and in the future work, we have many directions. So we want to try this experiment with the Internet of Things communications, such the LoRaWAN or any other. So we have to solve the problem about the terminate the communication in the right time, because it's not so easy as calculation. You have to think about the data consistency and so on. The second, we want to more push on the reduction of incoming energy, because current solution is pretty big. So we want to reduction and obtain energy for the smaller tip. And the last one, we want to try to push hard on the finding method to reduce power consumption of the system itself. So we want to find solution with the no tens of microamps, but ones of microamps and maybe a little more, less. Okay, thank you for your attention.
Congratulations, Michal. I even did not manage
Okay.
to raise the.
So you said
3
1
minutes.
minute.
Yes, so we have time for questions, please.
What kind of piezoelectric you have used?
Yeah, I don't remember the type. It's I don't have the photo here. I think so.
Is it ceramic or is it plastic? What?
Yeah, it's a plastic one.
PVDF maybe?
It's possible. I don't remember.
It's supposed to be some dual layer because it works on bending bone.
Yes, yes.
You simply cut, this buzzer because this buzzer is also working on
Yes,
flexion
yes,
bone.
yes.
That's it. If you manage without cracking. More questions? Please.
You excited the transducer by using an electric motor in your experiments, but how do you what will be the actual excitation source in practical applications?
In practical way, we can thinking to apply it on some electric motors, big electric motors. So in the practical way, we are applied some weight, and if we do some vibration with a big machine, after that we can generate some energy. That's our.
Okay.
And what's the voltage magnitude obtained directly from the transducer?
Yeah, it's here. It's about 30 volts.
Okay.
More questions? I had similar question. Yes, you are hitting it periodically and it should generate huge amounts of energy. But I've seen applications with Zigbee power switch when you want to control the electricity. So there are power switches which you press.
Okay.
And there is enough energy not just to press and to read the switch position, but then you can rotate in order to adjust the color temperature or intensity. Okay. So can you imagine measurement, reading the sensor, communication, and communication almost continuous because you are rotating and it is communicating with Zigbee. Why you have chosen such application? Because such application, it does not show you how much energy with one action you can generate. Then you can say, okay, we have collected 10 joule and with this we can do this and that.
Okay, that's a good question. So in this study we are focusing on the major work is in the is here. It's in the firmware. We try to optimize the firmware. We didn't fully thinking about the amount of energy as input. We try to optimize the output. So I think in the future we won't try to shrink the solution. We want to specify the amount of energy on the input.
Okay. Thank you.
Okay, thank you.
Congratulations. And this is not all today. What if you are designing some electronics and you need to test it? So Sebastian Temich
correct.
will present design and identification function to reduce the computational resources on the testing process of the analog electronics circuit. So, Sebastian, floor is yours, please.
Thank you, Mr. Chairman. My area of interest is slightly different than all presented here in this conference. I'm focusing on design and identification function to reduce the computational resources on the testing process of an analog electronic circuits. To remind you, my name is Sebastian Temich. I'm from Institute of Electronics, Silesian University of Technology. This paper was prepared with Tomasz Golonek and Damian Grzechca. During my presentation, firstly, I shortly describe you the problem of analog circuit testing. Then I will go to the circuit under test, circuit of our choice, its description, functional parameters. Then I will go to the technological process imperfectness, simulation profile finally. And then I will describe you our method of testing using the regression models based on the output signal feature selections. Finally, I will share some results with you. Okay, analog circuit testing problem. As you know, digital circuits has their own standardized method of testing where in the analog circuit there are no standardized methods, because we've got many outputs, many output forms, many functions, many specifications of these circuits. So researchers divided the problem of the testing into two parts. The first part is fault-driven test, when we are focusing on checking which element of the circuit is fault, and what's the impact, what's the influence of this faulty element to all circuit performance. In the second way, more popular in nowadays, we've got specification-driven test. It doesn't matter whether some element is faulty or not. We are only measure the specification parameters. If they are in its tolerance range of the circuit pass the test. If not, it not pass the test and go back to the technology line. The circuit of our choice is charge pump circuit in the Dixon architecture. As you can see on the right side, it is built from NMOS and PMOS transistors in 50 nanometers technology. Power source, input, and the output function. The functional parameters, the specification parameters which we try to measure in the circuit, in the Dixon charge pump, is gain of the circuit with nominal value presented here. Load dependent losses measured with 100 kilo ohms load of the output with nominal value presented in the middle of the table. And the third one is the power consumption, nominal value presented here. There are many different faults that may occur to the circuit, including the production line, including the lifetime of the circuit. In example, spot defects, shorts or opens in the circuit, thermal effects. We are focused on the technological process imperfectness, called the photolithographic mask deviations. It means that the photolithographic mask can move in the process of production of this element, and it may cause the change in the width and length of all transistors which build the circuit. In our research, the photolithographic mask moved from -5% up to 5% of its nominal value. So the width and length of the transistor may change from 0.95 of the nominal value up to 1.05 value of the nominal value of the width or length. The simulation profile, of course, we don't have the circuit. We've prepared simulations only using simulation software. In the simulation software, we've created 100 different analyses of the circuit. It means 1,000 different faults that may occur during this technologic process imperfectness. The transistors are simulated using best-in-4 models, represents 50 nanometers MOS technology. The circuit is sourced with 3.3 DC voltage, and the circuit is stimulated by pulse waveform from 0 to 3.3 volts with period times equal to 20 nanoseconds. Our idea, to test the functional parameters in comparison to the classic approach. In the classic approach, you've got different stimulus. You stimulate the circuit, and from transient response of the circuit, you try to measure, using measurement devices, every functional parameter as you want. Of course, it's a time-consuming method, because you need to stimulate the circuit, install the measurement devices, check the first parameter, do the same for the second, etc., etc. Our proposed approach is trying to short this, because we stimulate circuit only once with the pulse waveform, and from the output, from transient response of the circuit, we are getting the output signal features, based on which the model of regression is
created. This model or models of regressions allow us to calculate or to determine the functional parameters as we wish. In our research, we are focusing on 3 functional parameters, so we've got 3 models of regression for each functional parameter. Feature selections from the output signal, rising time of the output signal in transient domain, peak value, settling time, variance of the signal, settling minimum value, settling maximum value, and the mean value of these 2. These features allow us to create the feature vector X, as you can see here, based on which the regression model is created with the formula as here. In our methodology, we've created third order polynomial as the regression model, so it means that this k value is 3. We've got 7 different features, so n is 7, and we've got 3 functional parameters, so the m value is 3. And this formula, according to the third order polynomial, is as follows here. We've got coefficient multiplied by the first feature, the first feature in the power of 3, the second coefficient in the times of the first feature in the power of 2, and the third coefficient in the power of 1 of the first feature, etc. for the rest of the features, and to sum this up with the 3 coefficients, the BM coefficient. All coefficients were determined using the differential evolution algorithm. Population in the algorithm have 200 individuals, 2000 generation was performed, and the grading function is as here. We are trying to minimize the error between the target value and obtained value of the system. Of course, it's an offline method. That it means that we prepared all the simulations, all the responses and feature previously, and then we are trying to determine the values of the coefficients. First of all, we wanted to compare it with another model of regression, with the classic linear regression. Classic linear regression was determined, and the linear correlation was calculated. The value is presented here. Using our regression model, first order polynomial with coefficients as presented here, the correlation of this model is more than 99%. The difference between calculated and expected value, exemplary of course, are presented in the table below. Then we are trying to check what's the sensitivity of this method inside the tolerance range, because as I said previously, the circuit is unfaulty. The circuit passed the test when the functional parameters is inside the tolerance range. The tolerance value is 2%, so the circuit is unfaulty when the functional parameter is inside nominal value and minus 2% up and plus 2% toleration. Sensitivity of this method is 98%. We compared it with the support vector regression model, when the sensitivity of this model is 97%. Exemplary difference between obtained and correct value of the gain parameter is presented in the figure on the right. Constant line represents the true identification, and the dotted line obtained identification by our algorithm. Second, load dependent losses parameter. All coefficients were determined using this methodology. Difference between correlations. Linear regression model correlation is up to 98%. When we've got, using our methodology, we've got more than 99%. Difference are presented in here. Sensitivity inside the 2% tolerance range. Sorry, for P2 parameter, it should be here. we reached 99% of sensitivity, when for super vector regression it is near the 99%. Difference, as you can see, is here for the second parameter. And the third one, the last one, power consumption parameter, bigger difference between linear regression model and our proposed third order regression model, more than 10% difference, and our methodology is better. Difference in the exemplary values are presented here. Okay, efficiency inside the tolerance range. Here we've got only 0.5% tolerance range of the P3 parameter. Sensitivity 96%, where for the super vector machine is slightly better than our methodology. Difference, as you can see, are just a little bigger than in the previous two values, but the sensitivity is high as well. Finally, the time analysis, because we want to reduce the time of computations. The time required to determine all the features of the signal is 9 milliseconds. Of course, it was prepared and all calculations were performed using the MATLAB software, not implemented into the real circuit. Time needed to obtain all three functional parameters is summarized 5 microseconds. Overall time of the determination of the functional parameters is near 9 milliseconds. To compare it with the classic approach, when you want to determine all these three parameters in the classic approach, you need to stimulate the circuit twice. In the first, you need to stimulate the circuit to get the P1 and P3 functional parameter. Then you have to change the circuit by adding the 100 kilo ohms load to the output of the circuit and repeat the process once again to determine the value of second parameter of PLD parameter. So we reduce 2 times the time of the tests in comparison with the classic approach to test the Dixon charge pump circuit. That's all. Thank you for attention.
Congratulations. Good timing.
Yeah. Thanks.
Okay, now we have some time for questions. So anybody willing to ask the question, please? Then I will use
Okay.
my chairman's position. First of all, 50 nanometer technology versus what is reported nowadays, 5 nanometers. Why is that? It is normal for analog circuits to lag behind the digital ones?
Yes, analog circuits technology is not increasing or decreasing the technology as in the digital circuits. We've got the 50 nanometers technology, and also sometimes 90 nanometers technology is used in analog circuits. When, as you said, in the digital circuits we've got 5 nanometers, and we want to get it lower and lower. So it's, as I can say, it's typical values of of this technology.
Thank you. One more. You are using for excitation 20 picoseconds rise time.
20 picoseconds rise.
But the higher is the slew rate of the excitation signal, the higher is the maximum current, which might damage your circuit.
Yeah.
And in future application, when the driving signal will be not yours, but coming from internal circuit, it will never be 20 picoseconds.
Yes.
It will be much slower. So why is that? What you wanted to
I agree. It's some kind of difference between the concept as I present here and the future application into the real circuit. So of course, I presented you the concept, and we choose in the simulation process the stimuli like I presented
So
here.
it was only simulation here.
Yeah, it was only simulation, and
okay.
you know, the simulation is slightly
Can hold
different
everything.
than the real stimuli. Yeah.
Okay, thank you.
Okay. Thank you.
No more questions? Then thank you.
Thank you.
Okay, what else is left? Photovoltaics. We haven't thought about photovoltaics. And Davut Hadari will present us the performance assessment of high gain single switched boost converter for photovoltaic based residential application. So those
Yes.
who are looking forward to install some photovoltaic batteries on your roof, you should listen to this presentation. So floor is yours.
So, well, hello everybody. My name is Davut Qaderi. I am an assistant professor in Electrical and Electronics Engineering Department of Bursa Technical University in Bursa in Turkey. This study is presenting a DC-DC boost converter. My main area of interest is power electronics, especially I'm working on DC-DC converters and DC to AC converters for inverter structure and controller for structure. This study is presenting a DC-DC boost converter that can enhance the DC voltage to a higher level. So it is be the boost converter, and also it is not only is applicable for residential application, residential based application. It is suitable for all kind of structures that you need to a boost converter. For example, in electrical vehicles or in battery management systems or any other area that you need a boost converter. In this study, I'm going to present you the proposed DC-DC converter that not using a transformer. So the special losses related to these transformers is not will be our proposed converter. Also, the DC gain of the structure is considerable. For example, in the duty cycle of 90% for the power switch, we will have around 38 times of input voltage at the output ends. Beside, we presented a new structure of switch capacitors connected to the output of this boost converter to enhance to this DC voltage to 2 times. Okay, I will talk about this structure also, and also finally a wide group of simulation in MATLAB Simulink has been done, and also an experimental result will presented by applying a PV panel with around 200 watts, and the results are confirming the mathematical and the simulation results. In this figure, you can find the overall structure of a PV-based residential application. You have a renewable energy source and the PV panel that tops in the list of renewable energy sources. After that, the proposed boost converter to enhance this DC voltage to a desired value of the voltage. After that, we will have the inverter block to convert this DC voltage to an AC voltage for the home appliances or any other device that can work in 224 volt AC voltage in the grid side. Okay, so you can have the MPPT, maximum power point tracking systems, to fix this DC voltage at the output of converter, or any other type of controllers. Okay, this MPPT can track the maximum power point by the tracking from the inside and input and output ports of the converter. This study is focusing on the structure more and not on the MPPT algorithm. So in this slide you can find the proposed converter. The B sub-figure can show the proposed converter in several blocks of the switch capacitor structures, and the first one can show the proposed converter with only one block. This block, the first block, is the proposed converter, and the second block is the switch capacitor block. As you can see in the B sub-figure, these blocks, these SC blocks, switch capacitor blocks, can be extended to 1, 2, 3, and any of this structure can enhance the DC, the input voltage, to 2 times. For example, if you have 100 volt at this point, at the drain point of the power switch, at the output voltage, with consideration only one block, you can reach to 200, and if you apply the second one, you can reach to 400. The main advantage of this structure is that we have only one power switch, so the control process of the power converter is very easy in a comparison with higher amount of power switches, and also the structure for the switch capacitor block is simple, and by applying several power diodes and capacitor, you can enhance the voltage without any controller structure. This is the mathematical analysis of the proposed converter. It can be useful for researchers that would like to work on the controller structure. As you know, when you have a power converter that contains a power switch, the structure of power switch can be changed by in on and off mode of the power switch. So in the on mode, for example, here I will come back to this slide. I should say you firstly about this. As you can see, when the power switch is in structure in the converter, it means power switch is in on mode. Okay, the structure is another thing, and when the power switch is in off mode, the structure change. Okay, so we have to investigate our formulations, equations, to on and off modes. Okay, so I will come back to this structure, to these equations. This is very useful, especially for the sliding mode controllers, or PI and PID controllers, or any other type of controller that needs to transfer function of the system. Okay, so we have to find a relation between output voltage and duty cycle of the power switch. So if you have equation, by this equation you can investigate your controller structure to control and send desired and related pulses to the power MOSFET. Okay. In the first one, we assume that the power switch is in on mode. Okay. So we have 2 inductor and 2 capacitor for the first block. So it will be very interesting to find the derivative of current for the inductor and first derivative of the voltage for the capacitor. So and I reorganize them as can you see in the second equation in a matrix. So in the next step, for the 1 minus d time, or time interval, it means the power switch is in off mode. Okay, according to configuration, I investigated the new equations, so I found the final state of the converter in a matrix. So I combined all the currents of inductors and voltage of capacitor derivatives in a general matrix. So this matrix, the sixth one, can present you the final station of the final state of the converter. That, as I said, is very helpful for researchers that want to investigate the controller for the structure, because you can find easily the transfer function of the structure. For example, how we can reach to this equation. For example, if you consider this block, okay, when the power switch is on, okay, from here you can write a simple KVL in this block. So V input voltage will be equal on voltage on inductor, and by ignoring the voltage drop on the diode, you have a short circuit here. So input voltage will be voltage on inductor L1. So if you come back to the equation, L1 DIL over dt is V. So I reorganize the DIL on dt. So I, as you can see, Di also only is related to V in, as you can see. Okay, the organization of all of this matrix can be done by this way. Okay, as can you say, the off mode also is here for in sub figure B, and the final station of the first block can be found in this part for figure 4, as you can see. For continue of the this subject, I assume that as I said, we have two blocks. Okay, first block is the normal DC converter, and second block is the switch capacitor block. I am now focusing on the first block to read the reaction of the structure and investigate the voltage gain, and to obtain the voltage gain of the structure. As you can see, for obtaining the voltage gain, okay, we have to consider all voltage drops on all of power components. Especially the most of drops will be happen on the power diodes and power switches. And if you do a simple simulation or in experimental condition, if you consider, you will find the main of the voltage drops will be on power diodes. Okay, for this amount of voltage that I considered in this study, we are trying to convert 48 volt to 380 volt as the desired volt, DC desired volt. So for these rated voltages, the voltage drop on diodes is the thing about 1 volt. Okay, so if you consider this value of voltage, it did, and consider the VD as the voltage for the power component, it will guarantee that other losses, for example on inductors, will be smaller than this value. And here you can find the models of the study for the inductor with internal resistance or internal resistance of the diodes, and also in B subfigure C to subfigure C, you can find the state of the structure when the power switch is in off mode. So there is a very easy way to find the voltage, output voltage, and output voltage to rated to input voltage. For this, we have two inductor. You can find the voltage on the inductors. Okay, the voltage on inductors when the power switch is in on mode and in off mode. So we can find the capacitor voltage, and after that you can find the output voltage. And by replacing the 7 into 8, you can find the final equation of the voltage. It presents us the gain of the structure, and the SC block, as I said, enhance this voltage to 2 times. So it will be our final equation, where the normal boost converter, conventional boost converter, is 1 over 1 minus D. So the amount of the voltage gain is considerable in this study. Also, as I mentioned in the paper, you can find all equations for the fluctuation of the current for the, for example, for the first inductor, and also the value of how we can find the value of the inductor. For example, for V in, as I wrote in this table, V in is 48. Okay, V in is 48. V out is around 400 voltages. The frequency, switching frequency is around 100 kilohertz, and so you can find the parameter value. I tried to make the simulation and experimental results according to these values. Here you can find the voltage analog structure. It can be done in MATLAB Simulink, conventional boost, cascade boost, the proposed converter with only first block, and the general structure that we proposed. As you can see, for example, in 70% of D2 cycle, it reached to 20 as the voltage gain, but the conventional boost converter can give a thing about 2 till 3. And the efficiency of the converter, especially between 100 and 100 watt, is equal with the conventional boost converter. The level of currents is not very different from what you can see. So because of time, I directly go to experimental result. As you can see here, for example, for the 48 volt of DC voltage, we reach to 370 voltage in 1 kilohertz, 100 kilohertz of the frequency, and also the level of voltages and currents and the reaction of the power switch will receive the gate source voltages that can go to on and off modes, and as a result, I can show in this study we presented a this DC converter with SC blocks that can be extendable to more blocks and consist of several inductor, capacitor, and diodes. Work presented the on and off state of study, and also how I can say also the SC block can reduce the voltage and voltage stresses on the power switch. That can be one of advantages of the this converter. And finally, I should say that this work is funded by a grant, partially grant from the scientific research project unit of the Bursa Technical University in Turkey. Thank you for your consideration. If there any problem, question, I am ready to respond.
The problem was that you were over time, so please practice against the mirror or computer, so you end time. We have some time for short questions. Anyone, please? Okay. Go
Yes, please.
Can you open that last 3 slides?
Last 3 slides.
Yes, in conclusion.
Here.
Yes.
Yes.
Here you have written in one place that is a standalone, but later on it is written that power transmission to grid blocks. Which one is correct?
Which one?
That one place you have
In
written
comparison to classic boost converters, the SC base power boost converters
standalone in the 6th line.
Energy source based system operating at a higher voltage level, the both working in order to efficient for 6 line 1, 2, 3, 4,
6,
5, 6. Oh, okay.
And later on you have that given this, it is a power transmission to grid connected grid block.
As I said, yes, as I said, this is a general structure of this DC converter that can improve and can used in anywhere that you need to this DC converter. The reason that we entitled for residential application is that we are going to write a new project in our university, yes, and it is ready to give to our department. It is the beginning point of the this study and not another more.
One more technical question is there. Have you considered the capacitor outage or capacitor failure?
Yes,
for the switching?
As I think there is a question, we have an equation for that. You can find the equation, the duty cycle for finding this 308 or 400 volts. Okay, you can find the Olav equation in the paper. As you know, we have a very limited time. You can
I'm
find.
Sorry, I have to interrupt you because you haven't left any time for questions.
Yes.
So please follow your timeline next time.
Okay.
Thank you. We still have more interesting presentations, and Karol Olaf Piwowarski from Poland will present us the blocking characteristics of photoconductive switches. So note, these are not usual switches but photoconductive switches, and usually in high voltage application it is the desired property. And those are based on semi-isolating gallium phosphate and gallium nitrate topologies. So, Karol?
Yes, yes.
Floor is yours. And please remember
time.
The time. Okay?
I'm sorry. Duplicate.
Excuse me?
No duplicate, only clone, okay?
I didn't understand. Technical issues.
Sorry.
Thank you, Mr. Chairman. Hello, everyone. Today I would like to present research results of my colleagues from Military University of Technology and from Institute of Electronic Materials in Warsaw. It's called Blocking Characteristics of Photoconductive Switches based on semi-isolating gap and GaN materials. Outline. I will start with introduction of what is photoconductive semiconductor switch, PCSS in short. I will take its principle of operation, how it is built. Then I will talk about construction of switches used in our research. Then I will go to measurement results, and I will end with a conclusion. A PCSS is an electrical switch with its operating principle based on phenomenon of photoconductivity. It's made of semi-isolating conductor with two ohmic contacts, and the gap between and the space between ohmic contacts is called switch gap. The switch is excited by optical impulse, which excitates it and increase the concentration of charge carriers, which decrease the resistivity
of semiconductor. PCSs are commonly based on semi-isolytic materials such as gallium arsenide, gallium phosphide, silicon carbide polytypes 6H and 4H, and gallium nitride. What are possible applications of these switches? They can be used in power industry in hybrid power switch model. They can be used also in pulse system, in the application for military, in high power pulse lasers, microwave sources, terahertz signal generators, and in pulse systems for civilian use. For in automatic control module of electronic system. Here we have an image of tested switches. How do they look? We tested 3 switches, 2 made of gallium phosphide and 1 made of gallium nitride. The gallium phosphide switches were labeled GAP 369 and GAP 275. The gallium nitride switch was labeled as GAN 6187. What is worth noting is that GAP 275 switch was also subject of passivation, and the results will be shown in later. Okay, let's go to the measurement results. Here we have measurements in blocking state. As we can see, switches made of gallium phosphide for all measured range works pretty well, and for a gallium nitride switch, we can see that after voltage of 2,7 kilovolts, we can observe significant current leakage, when the characteristics start to be nonlinear. We can see that resistivity of GAP and GAN switches is different. This is expected because GAP material, gallium phosphide material used in a research had greater resistivity than gallium nitride. Here we have results of our measurements in conduction state for switch GAP 369. The measurements were taken by illuminating the switch active region by a laser, with by 375 nanometers laser, and the power was changed between about 1.5 milliwatt to 180 milliwatts. What we can see here is that for small amount of laser power between 1/2 to 3 milliwatts, we can observe much changes in conducted current. This can be explained by the fact that for the low laser power and for low laser power energy,
there's a change in laser beam shape. As we can see, there's little resistivity stays the same for all or three measured voltages, and after 3 milliwatts, it's almost linear. Characteristics is almost linear. Here we have conduction stand measurements for all three switches. We can see big difference in current conducted by gallium phosphide switch 369 and gallium phosphide 275 switch, and we can see between gallium nitride and gallium phosphide 275. As I said before, gallium phosphide switch, gallium phosphide 275 switch was the passivation was conducted on it, which as we can see increased the conducted current. Okay. We can see that the characteristics are nonlinear, and there's significant change in resistivity comparing it to measured in blocking state. Now the conclusion. In the blocking state, the current voltage characteristic of tested semi-oscillating gallium phosphide switches are approximately linear through the entire range of applied voltages. In case of semi-oscillating gallium nitride switch, the nonlinear current increases is observed when the voltage exceeds 2.67 kilovolts. In conduction state, the switch resistance remains high for all applied voltages. It should be noted that the characteristics are nonlinear. The electric field strength ranging from 5 to 10 kilovolts per centimeters has very small effect on the switch active region resistance. Passivation of the PCSS active region surface increased the photocurrent by approximately 2 orders of magnitude. The blocking voltages achieved for tested switches before occurrence of undesirable sparkling significantly limit their usability, for now at least. Thank you for your attention. I hope I will be able to answer your questions.
You can see questions have started before we get finished. Okay, please.
I would like to ask
yes?
Two things.
Yes.
What is the voltage drop on the open switch, and how depends the leakage current on the temperature? Because you didn't mention the temperature.
Yes, yes. All about the temperature. All measurements were taken in temperature of 300 kelvins. And what was the first question?
Voltage drop on the open switch. It's a very important parameter.
And you know this confusion that open in English is not the one that you
in state on switch, like this.
In conduction state, you mean, yes?
Forward voltage drop.
Yeah, the voltage drop when the
in conductive
switch is in state on.
Oh, okay.
Or it's open, maybe, I don't know, I'm sure.
Closed.
In state open, not closed.
On is closed because look at the dot drawing.
So off is closed.
This is our beginning of investigation. We didn't measure yet the drop on the.
But it's not so difficult to measure. Take multimeter and measure. And one more,
yes.
How would change the leakage current if the temperature would increase? because switches are heated.
How would
Leakage, the dependence of leakage current on temperature. You don't have this, but it's interesting. If the temperature would be high, for example, if in Celsius,
No,
for
not,
example,
not in conduction, probably, yes? In
yeah,
off.
no, when in state off, yeah.
no state, blocking state, right?
What will be
Blocking, yeah,
temperature
blocking.
dependence
Blocking.
of the leakage current?
Yeah.
Because the activity of the carriers, it is moderated by
Sometimes
the
on
temperature.
room temperature, the
I
leakage
see.
is very low, but on high temperatures it becomes very high.
We didn't measure it. We didn't make temperature measurements, but I suppose the leakage would be greater than the one we measured here. We have here.
Thank you.
Other questions, please? May I ask?
Yes, of course.
I'm quite disappointed. I was expecting that we will get the conductor. But you are saying that orders of magnitude change in the current, but here we have nanoamps, and in conductive state we have nanoamps. So where are those orders?
I mean, here we have linear axis, and we have logarithmic. So we have two.
So we have started at 10 in power of 2.
Yes, and we have 10
and
power
some
to
switches
4.
can
Yes.
jump up to
Very
10.
The one with passivation.
Very low current.
Power is 10 to the power 4.
But
Yes,
Yes.
it's about 1 microampere
10 microamps.
operating current on the switch, yeah. 10 in power 3 is 1 microampere.
Yes, yes.
There are switches for very low current, not for amperes, yeah.
Not
But-
yet. Not yet.
I have another question.
Yes.
You have promised at the very beginning that those can be used for laser control, even the terahertz electronics,
Yes.
but you haven't presented any results that confirm that. Because if you want to go to these applications,
Yes.
essential property is the reaction time.
Yes, yes.
And we haven't seen reaction time. So
Yes.
did you do those measurements?
Yes, we are doing it currently.
But do you have any preliminary results that would allow you to state that? That they are pretty fast? Because if you want terahertz, anyone can help me what it should be, not picoseconds probably, yes? No, femtoseconds. Terahertz.
By terahertz, femto, yeah.
Femtoseconds. So which device you will use to measure femtoseconds? Oscilloscope? Because if you want to connect the oscilloscope, yes, we all are accustomed that you can have the oscilloscope probe which can come up to 100 megaohms, but here you have gigaohms. Furthermore, for
Yes.
such frequency, megaohm, even megaohm
Yes.
oscilloscope probes do not exist. They are close to 50 ohm. This is it. And more or less they are differential. So I would doubt and I would exclude such statement, at least for the very beginning.
Okay.
But what is the future? It is just the beginning, because
Yes,
probably
yes.
you've seen the more or less photoconductive switches when you have the photovoltaic generation.
Yes.
And this photovoltaic is connected to the gate, and this way you can control the switch as well. But those are really slow.
Yes.
The reason is that photovoltaic until it develops and the currents are small, so until you charge the gate. So what makes you think that there will be fast switches here? What is the reason behind for the statement that you will go to terahertz electronics? What makes you think
What
that
makes
this
me
is
think?
possible?
We are not the first group who trying to study this photoconductive semiconductor switches. I've checked literature of other authors, and there are pointers that suggest.
But where are the physical reasons? Where are the physical reasons to expect much faster response than the classical device?
Well, we are. How to answer that?
Okay, so it's your homework.
Okay.
Okay, thank you very much.
Thank you.
And we are not finished yet. Still, there is one interesting presentation to do. And Jaromir Konečný, Czech Republic, is presenting a hardware approach of a low-power Internet of Things communication interface by an XP Flex I/O module. So, Jaromir.
Okay, thank you.
Jaromir?
Jaromir, yes.
Jaromir, floor is yours.
Okay, thank you. Hello, everyone. I would like to present our research hardware approach of a low-power IoT communication interface by NXP Flex I/O module. So my name is Jaromir Konečný and I'm from Czech Republic, University of Ostrava. So first motivation, what we actually do. So we are focusing in our research in low-power embedded devices. So low power is the main goal. So this research is focused on decrease of power consumption. So we have basically two ways how to make some algorithm on, for example, some communication. We have software implementation and hardware implementation. Software implementation is standard program like in C language or something like that, and we have also possibility to implement the algorithm in the hardware like FPGA or some special periphery like Flex I/O. So if we are running software, we are running on the CPU, and if we are implement the hardware implementation, we are running on some special periphery. So we do that, and we compare the results, and I will present to you. First, we implement communication protocol, well-known protocol RFC 1662. It's a binary-oriented protocol, and the protocol divides the message to frames, denoted with flag. It's a one special byte. To avoid the misunderstood of the flag in the data, we add some escape sequence. So this is the basically some explanation of the protocol. So we have some flag, then we are transmitting data, and the flag ends the frame. We have two possibilities: multiple frame, one flag, or double flag. It's okay. The flag cannot appear in data, so we have to replace the flag by escape sequence of two special bytes. So we replace it to 7D. But of course, misunderstood between 7E and 7D has been clear. So we have another byte here that denotes the right byte. For example, we have to transmit this data frame, and here you can see the special bytes which have to be escaped by this way, and finally we add some flag and we can transmit the data. So this is the basically communication protocol which we implement in a software way and in the hardware way. We can draw the communication algorithm into finite state machine, which have 8 states. So it's basically a little bit complicated. But if you imagine we're starting here, when we receive the flag, we are idle and we're waiting for the data into run mode. And when we receive escape sequence, this is 3 special states. And when we receive another flag, which is the final byte. Then we go to stop and then to idle, and we receive the whole frame. So software implementation was made in C language as interrupt routine. So if the CPU or MCU receive the byte, it appear an interrupt, and we process the data by a software C routine. I think this is well-known way. It's not interesting. The interesting thing is NXP Flex module is a special periphery in an NXP microcontroller. Basically, we can emulate the protocols or special hardware and something like that. The module consists of three main parts, which are shifter, timers, and pins. Input is uploaded to shifter, and the data are shifted to the output pin by the clock generated by timer. And we are also able to implement a finite state machine, which allows 8 different state, and the control is performed by central processor unit. So hardware implementation looks like this. So we have a UART, we receive data, and we have also current state, and basically on these two information we generate a new state, and we move data to output. So how it works? It's more detailed figure. So we have a byte from the UART. When the module receives 1 byte, it goes DMA request. So it's basically everything is DMA request and transferring to receive register and storage the variable to UART. Then the current data and the current state we are composing the comprises the address of the lookup table, which basically represents a new state, and the state is transferred to output pins. The pins are directly connected to the input pins, and we have some tricky thing here. We have timer, which is triggered by MCU pins, and the timer starts and immediately stops and create another DMA request, which move the information from the pin to current state. This is basically the function of the hardware implementation. So some results in comparison. We choose some 3 lengths of data frames. We choose 50 by 500 bytes, 1000 and 1500 bytes. Number of escape characters within the message, and a number of errors, because the error can appear if you have some unexpected byte following the escape sequence. So the table looks like this. So we can see the hardware. It's quite better. The time is smaller, and of course the energy is also smaller. So we save an energy. Basically, the average is about 37%. The best case was I just hope 72%, and the worst case was 13%. So basically, you can say that the hardware solution is better than software solution. In addition, in hardware solution, the processor can do another task. So this is the same same data, but another representation in graph. So you can see the bar graph of software implementation and hardware implementation. So in conclusion, we implement standard byte-oriented point-to-point serial communication. We make it as a software solution and hardware solution, and we compare. So FlexIO approach achieves better results in terms of processing times and total energy efficiency. Also, the implementation of the finite state machine via the Flex IO periphery allows the transfer of computational power from the CPU to special hardware modules, and the CPU computation power can be used to perform another task. So thank you for your attention, and if you have some questions.
Congratulations, probably the best time today.
Thank you.
You already have a question, please.
How you measure those times for both software and hardware?
We measure the times.
Yeah.
We just set some pin before and after that, and on the scope. Yes, on the oscilloscope.
Okay. More questions? Yeah, please.
Yep.
I have a question. What was the value of the clock frequency?
Ooh.
What you use, for example, in your hardware implementation and the software implementation? How many cycles you need to make the operation in your software implementation, and how many cycles of the frequency you need to make in hardware?
I don't remember the CPU settings, but it was pretty same. So we are using same clock frequency for hardware and software implementation, and it was basically on a KL28 processor, and I think it was standard, but I don't know. It was around tens of megahertz.
Tens of
Megahertz.
Thank you.
Okay. More questions? We still have 3 minutes to go. You saved the time. May I ask my question?
No.
Okay.
Yes, of course.
It was a try. Up to your explanation, you have gained both the speed and the energy.
Yeah.
But what you have lost probably is the chip area, because you have certain amount of the integrated circuit just dedicated for that purpose.
Yes, that's true.
Can you tell the percentage which is occupied by this machine?
It is basically different, like in a programmable FPGA, because this is not an FPGA, so you
don't even know.
You have,
if there is such information.
No, I can't say we occupied some percentage of the chip, because the periphery is on the chip. If you're using your choice.
Yeah, but otherwise it could have been dedicated to memory or to arithmetic logic unit, or just cut out to make your chip.
Yeah, I think that the future is to create the complex periphery which can be configured to some purpose, and you can save the CPU. So
yes,
this is the way.
But there are such chips which have FPGA on the periphery.
But I think
then
this
you
chip
can do whatever you want.
Yeah, this chip is, I think, cheaper, because FPGA is quite more complex integrated circuit. So this is a low cost microcontroller.
Okay, so any more questions? So we are finishing 1 minute in advance. Congratulations,
Thank
you saved our time. So thank you all, and don't forget one thing. You've seen 5 presentations, and there are forms to fill which one you consider is the best. So if you liked one of the presentations, go and do the vote. Thank you, everyone.
Thank you.
Congratulations.